Let's introduce the third speaker of the morning. He's Matthew Anel, and his talk on an example of an elementary infinity-topos.
Hello, everyone. Thank you very much for the organizer for letting me speak about my research here. And thanks to them again for organizing this conference. So my purpose today is to talk about infinity topos and in connection to elementary topos. So since the definition of higher topos, it has been an open question to know if the dichotomy between Grothendieck topoi and elementary topoi had an equivalent in the higher world. So there's no definitive answer yet. And there's a couple of definitions of what could be an elementary topos. And I'm not going to add a new definition. I just want to talk about something that could be an example, or at least you want to be an example. It does not satisfy, we're going to see the definition that has been proposed for an elementary infinity topos. But nonetheless, it's a very interesting example. And so that could be taken as a pretext to change the definition. Anyway, we're going to see. So let me start by saying that all the details of what I'm going to say today is in a paper on the archive. So here is the link. So the example that I want to talk about today is an analogy between what happened. Can you see the mouse if I do this? Okay. So in the world of one topos, it's known that, of course, the category of sets, of small set, is a Grothendieck one topos, and the category of finite sets is an elementary topos. And so in the world of higher topos, the category of sets is replaced by the category S, the infinity category S of homotopy types of spaces. And so there's not going to be any need for infinity topos in this talk. I'm just going to talk about the category of homotopy types of spaces. And so I'm going to rely on techniques based on homotopy theory only. And so it's a question to know what is an analog of finite sets in homotopy types. And so there's an obvious answer to this, which is finite spaces, by which I mean finite CW complexes. But as it turns out, this is not the good answer with respect to the structure of a topos. So we're gonna see that. A better answer is provided by another kind of finite spaces, which are the so-called truncated coherent spaces. So this is what I'm going to talk about today, and a large part of my talk is going to be about explaining and defining those coherent spaces. So as it turns out, there are two natural generalizations of finite sets for homotopy types, the so-called finite spaces and truncated spaces. So let's see what they are and what are the differences between them. So a finite space is just a finite CW complex, or it could be also finite, the realization of a finite simplicial set. And so examples include all finite sets, all the spheres, and most spaces that one encounters, like the projective spaces, the orthogonal group, unitary groups, Grassmannians, etc. And so they're very common. And that's why this is a notion that has been introduced. There's a lot of finite CW complexes around. The pi zero of a finite space is a finite set. And the other pi n's are not finite groups, but they are only finitely presented groups. And so in this sense, maybe instead of finite spaces, they should be called finitely presented spaces. And this subtlety between finitely presented and being finite motivates the following definition of coherent space. So I'm going to say that a space is coherent if all the pi n's are finite sets. And I'm going to call it truncated if it is more n truncated for large n, meaning that all the higher pi n's vanishes. And so truncated coherent spaces also go by another name, which is pi finite spaces. I choose coherent here because I'm used to coherent object, coherent sheaves, and coherent spaces, coherent modules, etc. So, but they could be called pi finite. It's a more kind of descriptive name. So here is, let's start by some examples of truncated coherent spaces. So they're somehow less common than finite CW complexes, but nonetheless, there are examples. So of course, every finite set is truncated coherent. Now, any finite groupoid, meaning if I have a groupoid object in finite sets, and I look at this as a homotopy type, then this is going to be a truncated coherent space. It's going to be a one truncated coherent space. So a particular example is the homotopy type of the infinite projective plane, which is the classifying space for the group Z2. And if you like this kind of thing, this is also the universe of sets of cardinal 2. More generally, if we have a finite group G, the classifying space of such a group is a one truncated coherent space. And if we have a finite family of truncated coherent space, we can take the union of them and we have another one. So for example, we can take the union of the classifying space of the group of permutations. And this is the universe of sets of lower cardinal. So more generally, any Eilenberg-MacLane space associated to a finite group is going to be a truncated coherent space. Now let's see now some examples of non-truncated, but nonetheless coherent spaces. So it's a bit bizarre examples, but since the higher homotopy of spheres is finite, then if we take sufficiently high loop spaces of spheres, we get spaces whose homotopy groups are all finite. And more interestingly, if we take a Kan complex with values in finite sets, then the realization of such a complex is a coherent space. And this is clear since the homotopy, if we have a Kan complex, the homotopy groups are subquotients of the value of the Kan complex. And so if the values are finite, the homotopy groups are finite. And now let's see some non-example of coherent spaces. It's a bit disappointing, but the spheres are not coherent spaces. I mean, it's obvious because the pi n of Sn is Z, which is not a finite group. So the category of coherent spaces, so let me skip this bit. So let me mention one result. Not only every Kan complex with finite value describe a truncated coherent space, sorry, a coherent coherent space that may not be truncated, but this is also necessary. So if we have a coherent space, then we can always present it as the realization of a Kan complex with finite sets value. So let me jump on the proof. And so let me compare now coherent and finite spaces. So first of all, the two categories of finite sets and coherent and truncated coherent spaces are kind of orthogonal. The intersection is reduced to finite sets. So no non-trivial CW complex is truncated coherent and vice versa. Now the category of finite spaces has several well-known universal property. It's the free co-completion of one generator for finite colimits in the world of higher categories. And the embedding of finite sets also has a universal property, which is a finite co-completion preserving the finite sums. Now, something similar exists for bounded coherent spaces. So let me say that up front. So the embedding of finite sets into truncated coherent spaces is an infinity exact completion. That's one way to think about those things. So I'm going to detail that later if I have time, but I wanted to mention that up front. So this is why those bizarre spaces kind of appear. So the category of truncated coherent spaces is also the initial infinity pre-topos, where the infinity here refer to the infinity categories. And it has also another initial property. It's initial for the pre-topos morphism, but it's even initial for a stronger notion of morphisms. Because as it happened, it has a subobject classifier and it is locally Cartesian closed. We're going to see that. And so it's also initial for morphisms preserving the subobject classifier and the dependent products. So I've made a table of comparison between finite spaces and truncated coherent spaces, and with a list of structure that they have or don't have. And so let's review this, and I'm gonna give the details on some of them. So first of all, both categories have finite sums and finite product. But only finite spaces have push-outs. It is not true that truncated coherent spaces have push-outs. And a counterexample is the spheres. We saw that the spheres are not truncated coherent. And it's possible to prove that there's no object corresponding to S1, which is a push-out in finite sets. Conversely, finite spaces do not have fiber products, but coherent spaces do. So there's a kind of additive multiplicative thing going on here between the two categories. The Postnikov truncations do not exist in finite spaces. The truncation of a finite space is not in general finite. But obviously they exist in truncated coherent spaces almost by definition. Stability by retract, it's known that finite spaces are not stable by retract. It's a subtle thing. It's because in infinity categories, the idempotent category is not a finite category anymore. It's a countable category. And so if we want to split some idempotent, we have to, this is a countable colimit. And so if we have finite CW complex and we want to split some idempotent, we may have to add a countable number of cells. And, but on the sides of truncated coherent spaces, they are stable by retract because the condition, because the retract of a finite homotopy group is a finite homotopy group. Finite spaces do not have exponentials, but we're going to see that truncated coherent spaces do. And a fortiori, finite spaces do not have dependent products, but truncated coherent spaces do. They are locally Cartesian closed category, which is very, very nice. The exactness condition, which in the world of infinity categories is dealt with the so-called Siegel groupoids. So I'm not going to say much about that. But essentially it doesn't work for finite spaces, but it does for coherent spaces. Now, on the matter of subobjects and subobject classifier, both categories are fine. Any subobject of a finite space of a truncated coherent space is again finite or truncated coherent. And they both admit a subobject classifier, which is just it's the Boolean subobject classifier. It's the set with 2 elements. But in the higher world, there's also the notion of univalent families. And so truncated coherent spaces have a lot of univalent family and have enough univalent families, which is not a feature of finite space. So the moral of this table is that somehow it should be clear that truncated coherent spaces have many of the features that we would like to work with. And the only drawback is the push out. And so that's kind of surprising and it's kind of annoying to do some abstract homotopy theory, because if we cannot build cell complexes, we're kind of unsettled. But nonetheless, the rest of the structure is so nice that there is something there. So let me, in the time that I've left, let me try to detail the exponentials and the dependent product property. Let's find sums, push out. Oh, let me first explain the fiber product. So a counterexample for the non-existence of fiber product in finite spaces is the loop space of S1, which is Z, which is not a finite set. It's not, Z is not a finite CW complex. And on the sides of truncated coherent spaces, we can prove that fiber product exists by some technique of homotopy theory. And more precisely, we have this lemma that if we have a Cartesian squares where any two of X, Y, and Z are truncated coherent, then so is the third. So this says that the fiber of a map, this says three things. The fiber of a map between truncated coherent space is truncated coherent. This says that the sigma type of a family of truncated coherent indexed by a truncated coherent space is truncated coherent, etc. So this is very useful property. And it's all a direct consequence of the long exact sequence. If you know this kind of things, I mean, you can, if one, so if two of the groups are finite, then so is the third one, etc. So let me go to the Cartesian closeness. So yeah, so the exponential. So a counterexample in finite spaces is this one. I mean, the exponential of S1 by itself is not representable because it has an infinite number of connected components. Now, so in bounded coherent spaces, we can do the following trick. So first of all, there's a lemma that says that if of course, in the whole category of spaces, the exponentials always exist. And so the question is whether the exponential computed in spaces is finite or truncated coherent. And so we use the trick using Kant complexes that I mentioned before. And so if I want to compute an exponential, and I just write y as the realization of Kant complexes with a finite value, but realization in the world of homotopy of higher category theory is just the higher colimit, it's just the infinity colimit. And so because this is an exponential, I can take it out as a limit. So this is an infinity limit of now powers of x, because the y-ends are finite. So this is finite powers of x. And so if x is truncated coherent, this whole diagram is truncated coherent. And so I have a cosimplicial limit of truncated coherent diagram. And we know only that truncated coherent is stable by finite limits. Oh, sorry. And so here we're going to use a trick that since x is truncated, so are all the finite powers. And so we have a cosimplicial diagram of truncated spaces. And for those diagrams, the beginning of delta is coinitial. And so we can replace this infinite colimit by a colimit index by the truncation of delta. And now this is a finite colimit, so finite limit. And since our category has fiber product and a terminal object, we have all finite limits. And so those exponentials exist in coherent, truncated coherent spaces. And now the trick is to use this to prove that this is locally Cartesian closed. So here is the sketch of the proof. In case of a finite set, we can use that the slice category of truncated coherent spaces over X is just a power of this category. And so it's Cartesian closed because it's a product of Cartesian closed categories. So here I'm in infinity categories. I forgot the prefix infinity, but it works the same. And from there, we can again use the trick to describe X as the colimit of a Can complex with finite values, and then we use descent. So this is where we use the fact that the category of spaces is a higher topos. So I'm not going to have time to explain the descent property, but essentially by using descent, we can write this slice as a limit of slice over finite sets, which we have proven are Cartesian closed. And so we have a limit of Cartesian closed categories. And now it's well known that the limit of Cartesian closed categories, again, Cartesian closed, because being Cartesian closed is monadic. So that's the idea to prove that S is locally Cartesian closed. So let me go over the exact completion and the sum object classifier. And so let me give a description of the final result. Yes. So it's possible to build within the category of all spaces a universe which is univalent for the smaller category of truncated coherent spaces. And essentially the trick is to take a big coproduct over the isomorphism classes of truncated coherent spaces. And then we take the classifying space of fibrations with a given fiber X. And so here we have to prove that those guys exist. Sorry. And so I'm running out of time here, so maybe I won't say much and leave the details for the questions. But nonetheless, the theorem in the end is that so this Lex category has a universe which is representable in spaces, but which is a coproduct of objects in truncated coherent spaces. So we have this theorem that we can always, we have enough univalent families. Sorry, I'm going a bit fast here. And this universe, it provides an example of a universe which is univalent and which is of course stable under sigma and pi, which is essentially the locally Cartesian closed condition and the lemma about fiber product that I mentioned before. Okay, I think I'm gonna stop here.
Good, let's thank the speaker. Questions or comments? There is one there.
Thanks. Hi, Mathieu. Thanks a lot for the talk. Also, a great paper. It was a joy to read it, especially because it was very startling to me, and it still is very startling to me, and therefore I don't really know where to start. So let me just ask one open question, and feel free to riff off that in any direction you want. And it is about the homotopy groups, really. I'm a bit confused about the role of homotopy groups here. So generally speaking, the homotopy groups cannot even characterize equivalences, right? So why would we expect homotopy groups to characterize the notion of finiteness that is relevant for the definition or the characterization of elementary toposes? Does that question make sense?
Well, okay. So first of all, these are homotopy groups of spaces. I'm not saying anything about homotopy groups of objects in an arbitrary infinity topos. So this is
sure,
everything here is very, very specific to the example spaces. Now, I don't know what is a good answer. I mean, because it works. Because if we impose this condition, we get a nice structure. Now, why is this condition on homotopy groups natural or interesting? I don't know. It's a bit bizarre. I mean, I used to think that those spaces were very. I used to dismiss a lot those spaces with finite homotopy for a long time, until I realized they were locally Cartesian closed categories.
Is that manco that they're not closed on a pushouts maybe an indication that we have to look for a third candidate, or do you think it's the right candidate, but we have to rethink the properties of an elementary topos or something like that?
So I don't know what should be an elementary topos, nor if there is an interesting notion of elementary infinity topos. It's not clear. I mean, it often happens that when we try to generalize a notion in a context, there's several candidates to be a generalization. So I don't know. It could be that the notion of elementary infinity topos is not unique, and that one of them may not have pushouts, which would be a bit disappointing. But since we have this example, we have to deal with it now.
All right, thanks.
Is there any other question in the room? Yes.
Hello, thank you very much for the talk. I was just wondering about the lack of pushout in your example. Is this related to the absence of some inductive types related to the internal language that we should expect to get from your example in terms of type theory, or am I missing something?
No, that's correct. So typically the inductive definition of the circle won't work. It won't produce anything in this model. But some other inductive constructions, like quotients of an equivalence relations or something like this, can exist. And so there's going to be a restriction on the kind of inductive type that we want to define here.
Okay, thank you very much.
Anders, I understand you have a question.
I'm not hearing the sound.
No, wait, we are not hearing him either.
You hear me now?
Yes.
Okay. Is the loop space of a finite coherent space finite coherent? It's an exponent, but
yes,
the exponent is a circle.
Yes, yes, exactly. The loop space of a coherent space is coherent, and if it is truncated, the loop space is of course truncated. So yeah, that's one of the major thing with the definition. So can I share? There's one slide that I didn't show, and I could, because there's a nice definition of truncated coherent spaces, which look like the definition of Koratowski finite objects, and that I think is an answer to Anders' question. So yeah, here it is. So I can define a space to be zero finite if there exists a surjection from a finite set. So this is just a fancy way to say that the pi zero is finite. And then I can iterate this definition on maps and using diagonals. And so I define a map to be zero finite if all the fibers are zero finite. And so if all the fibers are finite pi zero. And then I define a map to be n finite if all the diagonals up to n are zero finite maps, which mean that all the loop spaces are finite pi zero. So this is a definition that makes sense internally to a one-topos or to an infinity-topos. So in a one-topos, this just gives back the notion of a finite object. And we don't need the higher diagonal, just we need only one diagonal to get. After that, all the diagonals are isomorphisms, so the condition is null. And but in an infinity-topos, this gives a nice notion of a finite object. And of course, in the definition, this definition makes clear that the loop spaces, this notion is stable by looping. And that's why it's more interesting than finite CW complexes, because it's known that the loop space of a finite CW space is not a finite CW complex.
Okay. Paul Taylor has a question. Paul, are you still there?
Yes, I'm trying to turn on my camera and my mic. So it's a bit of an open-ended question, so I may be out of order given your time. Personally, I get vertigo from higher category theory. The question is that in the one dimension where I'm happy, there's things like suborbital classifiers and function spaces and so on, which are of interest to logic and are more interesting kinds of algebra than the kind which is generalized in higher dimensions. I'm wondering whether you have found generalizations of these things or more interesting logical structure in higher dimensions. Other things that we might call logic rather than just algebra that happen in higher dimensions.
The sound was kind of bad on my end, so I'm not sure to have the question right, but there's a lot of algebras that can be done there. I mean,
I don't doubt that algebra. I'm just wondering whether there's algebra of a kind that we would normally call logic, but in higher dimensions.
So I don't know. I'm not sure I understand the question right, but one feature of this model is to have the so-called univalent families, yes. Which will not exist in one categories. Yes. So you have classifying spaces for groups, and they are one truncated types, so they do not exist in discrete types or in one categories. And so you have nice models of pieces of Martin-Löf type theory provided by these guys with the univalent axiom. I don't know if this is an answer that you like, but.
Okay, let's thank the speaker again.
Thank you.